Hey everyone, welcome to the new week of oh wait, no, I'm now recording mini lecture. Today we'll actually be going through a midterm problem on Max Flow. So I actually just came out of the midterm and now I'm doing this, so very happy to be here. Hopefully you'll get something out of this thing. So when I study for midterms, I just want to get right to it. So let's do just that. I'll give some intuition, but most of all, just get right to the problem. All right. So I hope you can pause and read the question. All right, pause. All right, you're back. You probably read the question. So let me just highlight a few things in this question. You're looking to pair up some pets and some humans together, and you want to do it in a way that they see compatible. All right. So this should remind you of something. This should remind you of a mini lecture problem that I think one of the awesome tutors that we have covered. This is very similar to the bipartite matching problem. So on the right side, you see already that this is a bipartite graph that you have two sets of nodes and all the edges are between them. All right, but here are some differences. This is one of the common strategies in designing algorithms. Most of the questions you'll see on the midterm or in general in life are very similar to stuff that you've seen before. So maybe it's a modification of some problem that's very classic, or perhaps it's just a reformulation of the same problem. Regardless, we see that this is very similar to bipartite matching, but there are a few modifications. First of all, we have these new constraints about how many pets and how many students each pet and student wants to meet respectively. This is new because previously we always assumed them to be one. We just wanted to pair them up for every human on the left side, we wanted to pair them up with a human on the right side. But now we're no longer satisfied with just one-to-one pairing. We want to pair n to 1 or 1 to n. And the way we want to do this is, well, we want to modify this graph somehow. And from bipartite matching, you probably already guessed that we need a source and a sink, right? And I want the source to be connected to all of the stuff on the left side, all of my students, and my sink to be connected to all of the pets. And what this does is it sort of ensures that every time you flow a unit from S to T, you get some edge from S to this student column, from student column to the pet column, and from pet column to T. And the only interesting part in that sort of construction is that you go through something in the middle. You go through something here that tells you which pair of student and pet is meeting. So first of all, we should know that as with bipartite matching, all of these arrows should be going to the right. And another thing to note is all of the weights on this middle section should be 1. What does this mean? Like, what does this indicate? So it indicates that every time I have a flow, it means I have some pairs, a pair of student and pet matched to each other. They're meeting. But what I really want is I don't want duplicates. So if I have student Alice and pet Bob, I don't want Alice and Bob to meet 3 times. Alice probably wants to meet different pets, so I should, I should grant her that wish. This means that every pair of student and pet can meet at most once. It's perfectly okay if you don't take this path, but if you do take it, you want them to appear only exactly once. All right. Now we're dealing with the left side. So I want to say that, I have all of these candidates for students, and for every unit of flow I flow into the students, I can look at the student here and I say, how many units of flow can it take in? Or what's the max number of units that could pass through S4? Another way to say this is how many meetings, how many different pets can I meet? How many different flows can I take on? Since there are two things we have, so there are also always two things that we have a grasp on: things coming into a node and things going out of a node. Once you're out of that range of things, you no longer have a grasp on that node. So already we see that stuff coming out of it is determined by preference. So stuff coming into it must be determined by the only other constraint that has to do with students, which is how many pets he or she wants to meet. So it's perfectly reasonable to say I can only have a max number of S4 things flowing into S4. This just means, this is the max capacity of of this node, how many pets I want to meet. And similarly, I have S3, S2, and S1. All right, so this is sort of the bottleneck in terms of determined by the first criteria. This is the first criteria bottleneck where I say I can't have any more than this, right? Now I go on to the second one, and you might be guessing this is going to have to do with the sink, how the pets are connected to sink, and you would be exactly correct. Again, the only two things we have a grasp on is what comes into the node and what goes out of it. Already we have that stuff coming into the node is determined by preference. This is determined by who can I flow from into a pet. And now the only other constraint that I have is regarding pets is that I want to meet at most PJ students, no more than this, right? So this means that what comes out of me, the maximum number of flow units that comes out of me should be at most PJ. So I just put in P4, P3, P2, and P1. Again, this is the idea of you have stuff coming in, stuff going out. And ultimately, this is all there is to this graph. That again, this is a bipartite matching sort of algorithm where you say, all right, I have these compatible things. Every time I flow across from S to T, I must go through something in the middle, which means someone has to meet, right? And now what's the actual criteria? Remember in bipartite matching, we said everyone can find a partner if and only if the number of units of flow we can flow across is equal to the number of people on the left side, right? And so this is similar. This is saying, what is the ultimate goal? The goal is I want a student to meet exactly S1 pets. I can't meet fewer than S1, right? Because of course I can always meet 0. Like I can just, this graph always works out. I can just meet 0 people, 0 pets, whatever. But we want to meet exactly S1, which means all of these edges at this cut has to be saturated. So this means that there has to be 4 flows going into S4, indicating 4 potential meetings. Well, I mean, not 4, but S4 meetings, S4 meetings. So now I just say if the flow in this graph, let's call it G prime, is equal to the sum of all of these SIs. This just means all of these SIs will end up, all these flows will end up landing. All the flows that come out of S will land in T. If I have this criteria, this means that all the students' edges have been saturated, all the students' needs have been met, and all these constraints have sort of been met because of our construction. Then we say, we can decide, we can do it. Of course, you'll need a little bit more justification than this, but this is the idea of the algorithm. Again, we're modifying the graph so that we address each constraint in some way. And the constraint is addressed either by stuff coming into the node or going out of it. And all right, that's it. So you might be thinking, this doesn't really, like, what is max flow here? Max flow is used as a black box here. It's a black box indicating that, if I have S amount of flow, that means S meetings have been arranged. All right, so now you see that number 2 is peeking around the corner. So the next video will be on part 2. It'll be a little bit harder, but the idea will be the same. Hope you enjoy this. See you in the next part. Hey everyone, welcome to part 2 of this question. So this is a huge upgrade. You get this, bigger boss that you gotta beat. Here, let's just run through some new information that we've gotten. First thing is now we're scheduling over 3 days. Now, there's an extra condition that since we have 3 days, we can't have more than n meetings each day. So you might be thinking, first thing you should think, how do I handle the 3 days thing? Do I make 3 copies of this graph? Or do I have 3 nodes representing the days? Or do I have 3 source nodes or 3, we have to do something with this 3. So let this, sink in, simmer in the back of your mind. Okay, now no pet wants to meet more than L students. So this is an indication that you want to sort of connect these days in a way that you can sort of still get a grasp on each day individually. All right. And now the ith student has indicated preference, and these are the exact same conditions. And this should be a hint that we don't really want to make a ton of copies of this graph over here, because if we make a bunch of copies, then we would have to, somehow link it up into the same node. But again, this is not rigorous. Maybe you're having a different thought in your mind. Totally okay. Just let it simmer. All right. And all meetings must be between compatible pairs. So these three are the old rules, and we have this new 3 rules, and all 3 rules are concerning this splitting up the scheduling over 3 days. All right. So well, let's just think about this. If I want 3 days, I have a couple of options. One thing I could do is, I make a node for each day. I say, this is day 1. Maybe I'll use D1, D2, and D3. Or maybe I'm thinking that I should make 3 copies of this graph, in which case, I'll have a 1 copy, 2 copy, 3 copy. And I don't know, perhaps you have some other thoughts, but regardless of what thoughts you have, the first thing you should do is throw out some ideas of what kind of modifications you would like to do. The second now is to look at how these implementations work with these requirements, see how compatible they are with the new added requirements. So let's start with the new 3 copied one, because this is the approach that I actually tried to start taking when I was taking this exam, when I was taking the class. So suppose I had these, three copies, and I say meetings need to be scheduled over 3 days. That's satisfied. Animal shelter can't hold more than n meetings in the same day. So I could say, oh, I don't know, maybe I'll take all these things, and then in the end I'll hook it up. Before I hook it up to the sink, I'll have some edge that says, okay, I can't have more than L meetings on the same day. Oh, more than n meetings on the same day. Okay, so I have these things. All right, well, what else do I have? No pet wants to meet more than L students on the same day. Interesting. Okay, so no pet. So I have these pets over here, and I want to sort of single them out. So maybe I have, I don't know, I take this pet, the same pet is like indicated in this, like, I don't know, black dot. I want to pull all these pets out, and I want to say, okay, I want these to, I don't know, I want these to, in total, not exceed more than L. But already you see a problem. The problem is that when we're dealing with this on this side of on the sync side, we get these 2 sort of disjoint things that we need to take care of. One is this M, and one is this L. And what this gives us is actually that this won't work, because I want to flow to the sink, right? I want to flow to this T. How do I connect all these things? If I connect, I want both of these conditions to be satisfied. So if I only connect one of them, then that's bad. But if I connect both of them, then it means I can satisfy this M condition, or I satisfy this L condition, because you can flow either way to T. That's bad, right? You want to make sure that this is an AND relation. You want to satisfy condition A and condition B. So this is already problematic. And I guess another reason why it's problematic is, maybe you're thinking, I can handle it on the left side, but on the left side, you're actually connecting these pets to students. So you'll have this like or and action, or this sort of problem there. So regardless of what you have here, there's going to be a little bit of trouble. So that's when I abandoned this approach, and I went on to this other approach that I thought of. But I'd be really interested in hearing if someone could make this approach work. I mean, all of these things I'm saying is like how I thought about this problem. So make sure you have, I guess, some sort of, I don't know, streamlined approach to how you come up with a bunch of ideas. You test whether they're compatible with the constraints that are given, and then giving an answer. So, okay, now we have this other approach. We say, all right, I have day 1, day 2, and day 3. And in the end, I want to connect this to a sync T, right? And now all I need to do is to check for compatibility. All right. So again, we want to make sure that these bottom 3 conditions we already know how to deal with. So now the only thing we don't know how to do is the first 3. So let's check if they work. 3 days is satisfied. I see the animal shelter can't host more than n meetings total on each day. So now I have these nodes, I can just connect them to T, and I say, well, since every path or every unit of flow I flow across will sort of represent one meeting between a student and a pet, that means once I flow into some day D, that means that particular meeting happened on day D. And I say, okay, of all the meetings that happen on day D, of all the things that went into day D, I want them to come out and be less than M, right? So there will be fewer than M meetings per day. So I'll just, put these arrows in and I put weight M. And this just means, of all the meetings, I want at most M on each day. All right, so this could be handled. Let's see if we get trouble with the last one. No pet wants to meet more than L students on the same day. So one of the nice things we have here is that we no longer have pets split across many graphs. We only have one node for each pet. So I could say, okay, of all the things, of all the days for each day that I have this meeting, for each connection between some pet and some day, for each day for a pet, I don't want to meet more than L students. So I put these, and what this tells us is, again, every flow to the right, every unit of flow flowing to the right means a meeting. And I want all of my meetings of P4 to satisfy the condition that, on a particular day, you don't meet more than L students. So again, I can do the same thing for each of the pets, right? And you just, put an L on each one. All right, so this is also satisfied. Let's see if we can make sure to satisfy everything on the that's on the bottom. All right, so we have each student, the ith student has indicated, so this we know how to deal with. So I have source and I put it into each student and I use these weights as before. The jth pet. Okay, now we have a problem here. Remember we said that I want, I want to make sure that each pet meets at most PJ students. But we see already that the output of P has already been taken. How do we deal with this? Well, we can think, the problem we had earlier was that for each pet, we had to make multiple connections to two different types of things, to the day stuff and the like else students on the same day stuff. But here, what we can do is actually, we take this entire, having technical difficulty. Okay, well, I take everything here and I just move it to the left and I'll copy the stuff that I just wrote. Oh no, I'm having I'm having technical difficulty. All right, let's see. What I can do is I can make a duplicate. See if I can do this now. Whew. Hold up. Let me just, guys, technology. Okay, hang on. I can move everything here and I can just make a duplicate copy of all of my P's. So I make them P primes, P1 prime, P2 prime, P3 prime, P4 prime. And what this means is now I want to constrain how many flow out of each pet. And I can do this by just saying, all right, I'll put these weights here. And again, you see this sequential action going instead of things happening in parallel. So this means that like stuff here is going to happen and stuff here is going to happen rather than like or, which was the problem previously. So now I can say that P4 wants to meet as at most P4 students, P3, P2, P1. Again, this is the idea that the number, all the things that you have a grasp on are how many things go into a node and how many things come out of it. So in this case, how many things come out of P4 indicates how many, what's the maximum number of students that the pet can meet. And the stuff coming out of P4 prime is how many students I want to meet each day. And stuff coming out of D means that out of these, for each day, how many meetings can I hold? And here, I can sort of imagine that this is the same stuff going on, where I just put 1 here, because I still have this constraint that between any pair of students, I only want at most 1 meeting to happen, right? Again, I don't want student A and pet P to meet 3 times because they've already met. So now we have a full graph, and we can check to see if all the things have been addressed. Meetings scheduled over 3 days, check. We did this with our D1, D2, and D3. The animal shelter cannot host more than M meetings. We have these M, okay. L, we've taken care of. And the last 3 we've taken care of by inheriting what we had from the previous question, but also doing this copy and pasting action where we essentially add 1 more constraint on the piece. So this is maybe a theme that when you want to have, I don't know, some constraint on a node, you only have a grasp on what goes into it and what comes out of it. If I want to have more constraints, what I can do is just make copies of that same thing and link it to itself. All right, awesome. So that's it for this question. Just for a quick recap, I guess what I want to communicate in this question is that the ultimate answer is one thing, but the way that you think of these answers is a different one. You want to think of the solution by first thinking of how to address like new criteria or new information that you're given that's in addition to some problem that you've seen before, because this problem is very much familiar. We've done this in bipartite matching, and we've seen a very similar problem in class. And so the whole idea is you want to think of some strategy to deal with the extra information, the extra constraints that you're given. And of those different strategies that you have, you might think like which one addresses the new constraints the most effectively. And for our case, it's this adding new nodes sort of approach. But you could well imagine that for a similar but different problem, you might have to copy the graph multiple times, or you might want to add some other edges or nodes, right? Okay, that's it for today. I hope this is helpful, and good luck on your midterm, and I'll see you in the next mini lecture. Bye, guys.